Welcome to the Explainer. Today, we're diving into something really wild. A mathematical claim so bold it tries to solve a problem that's been considered impossible for 200 years.
So let's kick things off with a big question. For basically 2 centuries, a whole class of math problems was put in the impossible to solve pile. No single perfect formula could crack them. But what if that's just not true anymore? The source we're digging into today claims they've found the way.
To really get how huge this is, we gotta look back. See, back in 1824, a guy named Niels Henrik Abel pretty much slammed the door shut on finding a one-size-fits-all formula for these really high-degree equations. Well, fast forward 200 years, and the source we're looking at claims a brand new theorem didn't just knock on that door, it kicked it wide open. All right, so let's get into this supposed dead end. What exactly was Abel's theorem, and why was it such a massive deal in the world of math for so long? So here's the gist of it. The Abel-Ruffini theorem proved that once you get to polynomial equations of the 5th degree or higher, there's just no general formula to solve them using the tools we're used to. Things like square roots or cube roots. Mathematicians call those radicals. And what that meant for 2 centuries was that the best we could do was get close with approximations. No perfect, exact answers. But now, our source material says that limit has been broken. And here's the really interesting part. It wasn't by finding some mistake in Abel's work. Nope. It was by completely changing the rules of the game.
I mean, listen to this quote from the source. It's pretty dramatic. The whole point they're making isn't that Abel was wrong. It's that his way of looking at the problem, his entire framework, has been leapfrogged by a totally new approach.
So what is this new approach? Well, it's called Ezouidi's theorem. And the claim is, instead of using a static formula, it uses a different set of tools, a kind of step-by-step iterative process. It builds the exact answer for any equation, no matter how crazy complex it is. So yeah, think of it less like finding a key and more like 3D printing a custom one for any lock you find.
Okay, so let's dig into that idea a bit more. Radicals versus recursion. The key takeaway here is that it's a huge shift in thinking, from searching for a static, already existing answer to using a dynamic process that creates the answer.
This table really lays it all out, doesn't it? On one side, you've got the classical methods. They hit a brick wall for anything degree 5 or higher, and you often end up with pesky numerical errors. But on the other side, the claim for Ezouidi's theorem is pretty staggering. Universal for any degree. Exact symbolic answers, and 0 error, because it's not guessing, it's calculating symbolically. Let's stick with that lock and key idea. For 200 years, classical methods were all about searching for a single, pre-made key that could open certain types of locks. Abel came along and proved that for the really complicated locks, no such master key exists. But this new method, it doesn't even bother looking for a key. According to the source, it just builds a brand new one from scratch, step by step, for any lock it's given. Okay, theory is great, but let's see this thing in action. The source gives us a really concrete example, solving an 8th degree polynomial. And here it is. Just look at this thing. This is the kind of equation that gives people nightmares. It's an 8th degree polynomial. And with the old methods, you'd pretty much have to settle for an approximation. But the claim here, we can solve it. Exactly. And the process to do it is really systematic. This isn't about some flash of genius or a clever little trick. It's a repeatable algorithm. You basically set up the problem in a new way, then you run through a series of calculations, one building on the next, and at the very end, the exact answer just pops out. All right, so now we're going to see the calculations fly by. Now, don't try to read every single line of these formulas. That's not the point. The point is to just watch the process. See how it methodically chews through the problem, step by recursive step. Each calculation just builds on the one before it, and it's systematically breaking down this huge, complex equation, taking it apart piece by piece, until all that mess is simplified, and what's left behind is the real answer. And there it is. After all that work, all that heavy machinery, the whole complicated structure just boils down to one. Single, elegant number, 1. But it's not just that the answer is 1. The theorem also tells us how many times it's the answer. It has a multiplicity of 8, which means the number 1 is the solution, well, 8 times over for this equation. And that's actually a huge deal because the source points out that this specific situation, a single repeated root, is something that approximation methods can really struggle with. Okay, so what's the big picture here?
If this theorem really does work for everything, just like the source claims, what does that mean for the future of algebra? Well, according to the author, we're not just talking about a new party trick for mathematicians. This is being presented as a fundamentally different and way more powerful way of looking at polynomials. Something that's universal, always exact, works even with weird cases like repeated roots, and, surprisingly, is actually conceptually simple once you get the hang of it. And that's really the big idea we're left with, isn't it? It leaves you with this really provocative question. If a mathematical wall that stood for 200 years could potentially be broken down, it makes you wonder, what other impossible problems out there are just waiting for someone to invent a new set of tools?